Thank you very much. I'm very much pleased to be invited here. It is an honor for me. And it's the first time that I am at Bonn. I'm just enjoying everything around. So the environment, the people here, everything is perfect. So thank you again. And what I'm going to tell about is the moduli space of a planar polygonal linkage. Let me start with the definition. So I will use the blackboard, and sometimes I will refer to the figures that appear over there. So I think that I will use consequently just one blackboard. Okay, what is a planar polygonal linkage? This is a very elementary object. So one should think of it as a collection of rigid bars that are joined at the endpoints by revolving joints. And so therefore, so this is the bars are rigid. Here we have revolving joints, so it is flexible. It lives in the plane. So let us fix the L1, L2, L3, so on. It is all defined by the vector of length L1, Ln. We assume by default that this collection of numbers, so these are all reals, that it satisfies the triangle inequality, so the thing can be closed. And this is the linkage. And by configuration space, by moduli space of L, we mean the set of all possible planar shapes of this guy. We allow whatever, self-intersections, self-overlappings, just whatever, to get a complete manifold. And of course, it makes sense to factor out the isometry, the orientation preserving isometries of the plane. So these are planar, and we factor out iso plus of R2. So that's the definition. And I would say, first I need to say that it is a very well-studied object. So there are many papers, and let me just list down very shortly what is already known. So the first thing is that if L is assumed to be generic, whatever this means, and I will talk mainly about generic case, just to avoid complicated items. So for generic L, M of L is a closed manifold. Closed manifold, and what is its dimension? It is the degree of freedom, and degree of freedom is obviously n minus 3. So it is an n minus 3 closed manifold, and it comes almost automatically with a smooth structure. So we can write here also smooth, or oriented. What is known about it? So there is an easy classification just by hand for small dimensional cases. 5, and it's a bit more complicated. 6, it's just by hands. Now for bigger number of edges, what is known there? Cohomology ring of M is known due to Faber-Schutz. The fundamental group, which is in fact a bit ugly. Well, I'll stop here, but one more important item is that this moduli space of L is canonically isomorphic to the space of stable configurations of points on the unit circle. Let me explain what is it. I will first write stable configurations of n points on S1 factorized. So S1 should be viewed as the projective 1, and the factorization goes by PSL to no, not C, R. Yes, R, of course. So what is that? So we take the circle, it is S1, and we put there n points. Each point, so the points are numbered, so there is some numbering, 1, 2, 3, 4, 5, 6, and the points are weighted. So each point is assigned a weight, and the weights are nothing but these lengths. So the weights are exactly the length. So the point number 1 has the weight L1. And so we take all possible configurations on the circle, including some of those when the points glue together. But we allow them to be glued, not too many, in the sense that if the points glue together, the condition is that the sums of Li's over this sub-index I should not be greater, should be smaller, actually, than the sum of the rest. So this is the condition, and this is how they. Because I want to treat on just generic case. So well, let's forget it, not a non-generic. Of course, there are results for non-generic cases, but just to simplify. Sorry?
You didn't say how you make the correspondence.
I did not say. Well, I did not. And I'm not going to, maybe.
Okay.
No. So assume, okay, well, I tell something about the correspondence. If I have this and a point from here, so it is a polygon. So I just map the endpoints of the vectors on the circle, and that is one way, it's clear. And the other way is not that easy, because when you take just a collection of points, then the corresponding vectors basically not necessarily sum up to 0. But because of this factorization, we get what we want. That is, in each, so this is not just one collection of points, but the entire equivalence class. And the statement is that in each equivalence class, there exists just one point which sums up to 0. It is up to rotation, of course, which is up to rotation. So this is important, but now we can forget this for a while. Okay, so let us. So this is important, but now let's erase that. Okay, and what I'm going to present right now is the cell structure. So cell structure on M of L, which resembles very much the Permutohedron. And surprisingly, there are some other classical polytopes that arise in this respect. One more property of the configuration space that, well, I should have said it before, that the configuration space depends on the length. Depends on the length. Coefficient in Z. No torsion, no. 3 abelian ones, so that they more or less, they not okay, no torsion.
Moreover, the computer the link, a homology link, not only so it's as a ring is no, it's much more than this.
Yeah. Yeah. And yes, well, everything is different.
Introduced by what's his name,
Kupilatsa? Oh, really?
The one other way to do this. Yeah, he invented this theory for pure combinatorial algebraic reasons, but turned out the right answer. Yeah.
Well, so the elementary conclusion of the discussion that it is not necessarily a sphere, and Permutohedra are all combinatorial spheres, so we cannot expect exactly Permutohedra, but we get something very, very much related. And so the the first thing that I want to do is to remind you about combinatorics of a permutohedron. Let me shift it down. So this is P. This is P4, the standard permutohedron. So just no, because I am going to write it here. Well, I think that the majority of the audience knows about permutohedra better than me, so they do not need the picture. So the idea is that so I'm going to describe the combinatorial structure of it and how the labels appear on the faces of a permutohedron. So first of all, the vertices of the permutohedron are labeled by the elements of symmetry group. For instance, here we have a vertex labeled, say, 2, 3, 1, 4, and another one labeled by 2, 1, 3, 4. Okay? And now I do something which looks a bit artificial. I put curled brackets around each of the numbers. And I treat it as a ordered, linearly ordered partition of the set of indices into 4 non-empty parts, so to say. Now, we have edges of the permutohedron, and the combinatorics of the permutohedron says that 2 vertices are joined by an edge whenever the labels differ on permutation of the neighboring elements. Therefore, it makes sense to label an edge, to label the edge, this very edge, by the following. So here we permute these 2 elements. Therefore, we put here a set containing of 2 elements, 3 and 1, and then comes again 4. And then once you have an edge, you immediately can retrieve it at its endpoints. You just take all possible ordered refinements of this guy, and you get the endpoints.
So you're allowed to permute only the adjacent ones?
Yes. It corresponds to the edge structure. And moreover, there is something.
The question was, if you just write down the chain of numbers as this vector, when you sort of allowed to swap them, like 3 and 1, you're allowed to do it only for the adjacent.
Only for the adjacent. Well, all the labels appear there as vertices, but if they are not, if they are not adjacent, then they are not connected by edge. So it's combinatorial structure. And huh? Well, it's not Bois. No.
You consider all transpositions. No, that was my question.
Well, again, so the vertices are labeled by such guys. 2 vertices are adjacent. This means they are connected by an edge, if and only if they differ on an adjacent transposition. Therefore, the graph of the permutohedron is trivalent, because here you can permute here, here, and here. So there are 3 adjacent edges, and you can look at the picture and observe that.
Adjacent theory of symmetric group consider the transposition of 2 adjacent, or 2, 3, 4.
Oh, I see. Well,
this is because my question. Your case is not adjacent in that sense.
But if you switch to the coordinates, you will get exactly what you mean.
Yeah.
But let us forget. Let's not look at the coordinates. Or let's look just at the labeling. What's there? And there is a face adjacent to the edge. It is hexagonal, which is labeled by the following. So let's first put 2, and then 3, 1, 4. It's a 3-element set. And how do you retrieve the edges? You take all possible ordered partitions, so you can partition it in 6 different ways. So there are 6 adjacent. So you can easily read off everything, just everything. Okay. Now the idea. So this was Permutohedron, and what is written over there. So to summarize this and to generalize, the k faces. This means the faces of dimension k are labeled by ordered partitions of this set into n minus k non-empty parts. And the patching rule corresponds to refinements, just to refinements. Okay. So now I guess this all was clear, and I can pass to the moduli space. So the idea is the following: that I'm going to put labels on to associate labels to the moduli space, to the points of the moduli space of a linkage. So we fix a linkage. L is fixed, and we get the configuration space, which basically can be very complicated. So this is M of L. And I pick a point here. It is some closed polygon in the plane, just by definition. So we have a polygon, and I associate to it a label lambda, which is combinatorial thing. So there will be a finite number of different labels, and therefore the moduli space will split in the disjoint union of equivalence classes. So the points will be called equivalent if the labels are one and the same. And I should confess from the very beginning, but something very disappointing is awaiting you, because it is not universal. So universal means that the strata are as bad as possible, and in our case, something completely different happens. They are as good as possible, so the strata are just open balls, and they fit together nicely.
Stop me, so again, what are the strata?
Okay. And this is what I'm going. This is what I'm going to describe right now. So they come in a most elementary way. So let us assume, to start, that the point here, the P we start with, we start with a point. Now I'm going to associate a label. I start with a polygon with no parallel edges. Therefore, the edges are cyclically ordered by their slopes. Yeah, and therefore, what I arrive at is the cycle ordering, which for instance I can cut through the last number, say through the number 5, and I get the linear ordering. Well, something like that. So this is the labels. The labels is this one. It is cyclic ordering on the set of numbers from 1 to n.
Lengths of arc proportional to a.
No, there are no lengths. It's a combinatorial, just cyclic ordering. So no lengths, no arcs. And it's at no length at all. There will be no length further. Okay, and this was for polygons without parallel edges, but they exist, and assume that there are parallel edges. For instance, for this particular case, number 2 and number 4 are parallel, and so we have no ordering on their slopes, and therefore it's very natural, the most natural thing that we can do, that we put them in one and the same set, assuming that there is no ordering inside the set as usual. Well, actually, as usual. Now what I can let us notice the following: that if we are given a label, its preimage here is either empty or a ball, and the dimension of the ball can be easily retrieved by the number of sets. We shall give exact statement a bit later. And the balls, they they fit up nicely. They are of different dimensions, and they fit up nicely, and they form what is called a regular cell complex. This means that, well, a cell complex, this is something that you build by induction, starting with low dimensions, that each cell is glued to the already existent skeleton by some injective mapping. So it's, oh, I will formulate it right now. But before I formulate, let me tell you the following, that assume we have the polygon we start with.
You start from n minus 3 and you go down according to.
Okay. Then I can, if I put the edges keeping their directions, but in the order which corresponds to the slope order, then I necessarily get a convex guide over there. You see the convex polytope. And therefore, the necessary condition to label lambda to appear is that we cannot freeze together too many edges. So you see that edges 2 and 4 are frozen together in that in this very convex polygon, yes? And the message is that if the sum of Li's over some subset J, it is a index subset, is greater or is greater than the sum of the rest, then you cannot freeze these edges together because of triangle inequality. So there is some restriction. So not all possible labels of this type appear. And to summarize this, now comes the statement. Now comes the statement. Okay, no, this is not that yet. So we say that two elements are equivalent if the labels are the same and the equivalence classes are open balls. And now the definitions, so that we encount here only admissible partitions. And partition is admissible if this holds. This means that well, yeah, I'm sorry. Yes, indeed. So it's a partition, some sets, and so the total length of each subset should not exceed the length of the rest. That's clear. Okay, sorry. Okay, and so what we summarize here. So above is the description, combinatorial description of the Permutohedron, and the second part is the combinatorial description of our cell complex of the moduli space. And it looks like this. The k-dimensional cells, so k balls here, are labeled by cyclically ordered, admissible, that means this conditional Lex partitions, of the set into k plus 3 non-empty parts. In particular, the faces are the faces of maximal dimension, are labeled by cyclic orderings.
There's something odd about this fact that we have a cyclically ordered sets, on the other hand, it's a full permutation group. Maybe it's a permutation group up to some extent.
It is Sn minus 1. It is exactly Sn minus 1. But it but yes, but it's convenient not to refer to, because for Sn minus 1 it is not, it comes here in not a canonical way. Okay, and the patching rules are dual to those of Permutohedron. So what I propose that now we compare what happens. We compare the Permutohedron and the cell complex. So first of all, there are linear orderings for Permutohedron. Here we have cyclic orderings. For the cell complex of the moduli space, we have admissibility conditions. And in a sense, the patching rules are reverse. And this hints just that we should treat the dual complex instead of this one. Okay, now, okay, let me give you some easy examples.
But can you say a little bit more about the individual cells? Are they, because they're naturally polyhedra, right?
They are natural, not natural, they are combinatorial spheres, but they are polyhedra.
They look of natural, as far as I can tell, I might be mistaken, in this sort of movement, I think that it's called this kind of natural examorphic. Maybe I'm mistaken. Again, there is sort of a moment where here, but it's really toric varieties.
Oh, yes.
Moment where it collapse all, if I know I'm mistaken,
Yes, because
all the cells just with single polytope.
this is what I wanted to, well, oh, well, of course, so this is a bit of a secret, so I didn't want to take it was, so our moduli space are the real points of the complexification. Complexification is MON, is a closure of MON, and but what I'm going to talk about is extremely elementary things. So example one long edge. What does it mean? That we have a linkage, a polygonal linkage, which looks like this. So assume that there is one long edge, and the rest are of equal length, and it hardly closes. It hardly closes. Okay, so there's the rules. Our rules say that we should list all possible cyclically ordered admissible partitions. Assume that it is number n. So this edge is long, and therefore, if it should be in some part of the partition, and it cannot come together with any other because of triangle inequality. So any admissible partition looks like following. So there is a one element set where number n lives, and we can add nothing to it. And the rest can be any, just any. So the rest is any partition. Any partition of the rest. Okay, therefore, we automatically can cut the circle through this point, and we get a linearly ordered any partition of this guy. And the patching rules are basically the same as for Permutohedron. Therefore, we automatically get Pn-1 dual. So we get just the Permutohedron. Okay, this was the first. This was first. The second is also elementary. Second is the equilateral pentagon. Equilateral pentagonal 1, 2, 3, 5. Equilateral pentagonal linkage. And here we have what is called a transitive complex or something like that. So it is so the moduli space is a surface. Its dimension is 2, and it is a surface of genus 4, and it is patched of 24 pentagons. So the cells are pentagons. It is very easy to see, and they meet 4 at each vertex. So, for instance, you can take rectangular hyperbolic pentagons which exist, and you can pave the universal cover of this guy by just pentagons such that they project. Here it is. It is surface of genus 4, orientable. Genus 4. And the complex is very nice. Okay, now.
What we should say about the case when we have one long edge that which is a sphere?
Yes, as it was, yes, in the previous example, exactly. Sorry, I forgot to tell that. For one long edge, the combinatorics is that of Permutohedron, and Permutohedron is a convex polytope, so it's a sphere. Yes, exactly. So that was the case when it is sphere. Now we take equilateral with 2k plus 1, where n is odd. Otherwise, it is not generic. And this is something interesting. So all the cells of maximal dimension are one and the same from combinatorial viewpoint. And the message is that combinatorially, they are dual to cyclic polytopes. So duals to the cyclic polytopes. What is Cn? So the star stands for dual, n minus 3, that we take the space R3, we take the moment map, the moment curve. We pick n points. Yes, no. We start with Rn minus 3, sorry. And we pick n points on the moment curve. Moment curve is the curve x squared, and so on. It is a very, very classical object that if you pick n points there and you take the convex hull does not depend on the points you choose, and it is neighborly, and the polytope is neighborly. Let me not give the definition, but just say that it participates in the upper bound Macmillan's theorem. So it has the maximal number of faces for given dimension and for given number of vertices. So it is some
set of vertices less than n half is
yes n minus 3. If, for instance, n minus 3 over 2. If you take any set of vertices of smaller than this number, then they span a face. So it is a neighborly property, and so there is a huge class of neighborly polytopes, and cyclic ones are just a subclass. So it's combinatorially, it is just one point element here, and so it is more or less. Well, it's not that difficult to prove that.
What's claim that if you have n,
if I take an equilateral linkage with odd number of edges, then all the cells of maximal dimension have one and the same combinatorial structure because everything is symmetric, and so each cell has a combinatorial structure. So its boundary is a combinatorial sphere, and the combinatorics of the boundary is exactly C star of n cyclic. It's dual to the cyclic.
and what's the global type of the manifold?
Oh, well, it is something. I don't know how should I express that.
Hard to say, yeah?
Well, it's many-dimensional manifold, so there's no classification.
There is one can take Farber and company and read both Homogeneity and
Yes.
try to guess what it is, but I don't think anybody really knows. Maybe Kamiyama knows, but maybe not. This is because it's some kind of a remarkable manifold.
Yes,
God knows.
It's clear that this distinguished manifold
It is
must have some group,
It has a nice
group
name.
attribution.
But is there any other place where it is?
Yeah, for a small n, we know kind of know.
For small n, yes.
Like why surface of genus whatever 4 is more remarkable than surface genus 3 or 5. It's kind of very much unclear.
Okay. Well.
So how 4 is better than other numbers? It's very strange.
Okay.
But again, it's possible that there's some other descriptions. Yeah, again, it's, there are other ways to describe this thing, sort of surgery and so on, but it's, again, the
Okay.
Okay, now let's pass. So this, in a sense, if we take the moduli space of an equilateral linkage, it is. No. If you.
Well, there are formal manifolds. I don't know, but
What was the question, please?
it's a real set of real points of some remarkable Kähler manifolds. There are even more remarkable Kähler manifolds, which is a real point. I mean, not just Kähler, projective, smooth division, right?
Yes. Oh, okay. Well, the point is that this guy, not this guy, but the configuration space of this guy, is in a sense universal for all configuration spaces, because each configuration space embeds here for sufficiently large n as a subcomplex. And this allows us to say the following. So assume we have any generic linkage. Then each cell, so again, let's go back to, so now L is any generic one. And now we have, again, faces of different dimensions, and they are combinatorially different. But the point is that each cell is combinatorially a face of that C prime n, but there should be not that n but there should be some other n minus 3, n minus 3, where n is much bigger than n, basically much bigger. The second observation, each cell for generic case is a simple polytope. Simple means that the dual one is simplicial. Is a simple polytope with at most k plus 3 facets, which is almost obviously, if you look in details in this combinatorial structure, we'll derive it, you get it just for free. And here comes a universality property that assume we are given a simple polytope with at most k plus 3 vertices or faces. So that is a typo. With at most k plus 3 faces, I'm sorry. It arises as a cell of the cell complex for some polygonal linkage L. So everything arises in this way, and this is the Gale diagram technique involved, and it's a simple fact if one knows the Gale diagram. So it follows immediately. Okay. Okay. It was about the original cell complex, and now, as we have seen, its structure hints that we should pass to the dual complex. So starting from now, we are going to discuss the dual complex. So we had a complex, and we dualize it just in a usual way. And now we get to even better object. So here are its properties. So each cell is a Cartesian, is a combinatorially is a Cartesian product of permutohedra. Permutohedra is what we described before. And these permutohedron was the one which appeared on the very first slide. That's it. So classical permutohedron. And the point is that for each n, so I described some combinatorial structure, and it can be realized as a convex permutohedron, and moreover, there exists the canonical permutohedron for each dimension. That is, you take the vector 1 to n, it lives in Rn, you permute it by all possible permutations. So you take its orbit with respect to the natural action of the symmetry group, and you take the convex hull. So this is the permutohedron. So this means that now I'm talking about a metric object. It's a metric canonical permutohedron. And what is nice about it? the faces of the permutohedron, of the canonical permutohedron, are Cartesian products of lower dimensional canonical permutohedra. So this is not just combinatorially, it's metrically. For instance, the hexagonal faces are permutohedra P3, and the quads are products of segments. Two segments, segment is just P1. Okay, the point is that this all goes metrically. And therefore, if we have something, okay, here it is, which is composed by products of permutohedra, you get a PL structure just for free, because you can realize each cell as the Cartesian product of the canonical permutohedra, and then they fit together face to face in the metric sense just for free. And it is not all the PL structure that I'm going to tell, but that the entire construction can be realized in the Euclidean space as a surgery, some surgery on the permutohedron. So we are going to get something which can be called, up to some extent, a polyhedron. So we are going to realize the moduli space together with cell structure as some polyhedron, which of course is not supposed to be convex, but which will be, well, let me go into details. Now, how does it go? Oh, no. Let's start. Let me explain it on the blackboard first. Okay, we have the configuration space M, the moduli space, and the dual cell complex. And now let me remind you that the vertices, so this is a dual set complex, that since it is dual, the vertices are labeled by cyclically ordering permutations on the set from 1 to n. To the dual, yes. So there are exactly n minus 1 factorial vertices, and they correspond bijectively to cyclically ordered permutations, to cyclic permutations. Okay, so now I want to define a map phi, which maps the vertices of the dual complex on the moduli space to Rn. Actually, it will be not Rn, it will be the vertices of the standard permutohedron Pn minus 1. How it goes? So we pick a vertex from here. It is something like this. Something 1, 2, 3. We take its label. So let me write that it belongs to here. What I do, I cut the circle through number n. So I single out one particular number, let it be n. I cut the circle through here, and I get a linear ordering 1, 4, 2, 3, 5. And it is a label of some vertex of the permutohedron. So here is phi. Here how it works. And so we have already realized, so we have some vertices here, a collection of vertices here, and then we just map them by in such a naive way to the vertices of permutohedron. Now we treat the faces one by one, starting from lower dimension. What does it mean? That I take an edge here, and I look at the images of these two vertices here, and since there is an edge, I put in an edge here, and so on and so forth. So for instance, we have 4 edges here, and these are the pre-images of these 4 edges. And here we have a rectangular, a polygonal planar face. I patch it there. And nice is that I always can do in a proper way. This means that if I have something polygonal here, then these 4 points, they lie in one plane. So I can patch in something which is really planar. So I do it in a very naive way, and the point is that I can do that successfully. And there is one more way of describing it. So we can start with the standard Permutohedron. So let it be P n minus 1, this is it. And what do I get? Sum of faces of the Permutohedron correspond to faces of the configuration space. And then I keep them. But it can happen that a face corresponds to nothing over there because of corresponding partition is non-admissible. Then I just remove the face. And what I get is the Permutohedron with holes, but there is something else that should be replaced, something which are so-called diagonal faces, which arise here because of this the cyclic ordering. For instance, here you cannot interchange number 1 and 5. In the Permutohedron, if you interchange 5 and 1, they would not be joined by an edge, but there they possibly will. So there is some very explicit procedure on the Permutohedron. So you remove the faces that do not survive. The rule is quite simple, and you patch in the sum of the diagonal faces, and again we know which ones. So this is, for instance, how it goes for the example we have already seen. So the equilateral pentagon. For the equilateral pentagon, we start with P4, so the Permutohedron which appeared on the very first slide. So the one skeleton survives completely. All hexagonal faces die. Quads survive. And what new appears here is the 4 hexahedral cylinders. So you take 2 opposite hexagonal faces, they are removed, but instead you patch in the entire cylinder. It is over there, so we can see. So we get something which is self-intersecting, but you can deduce easily that what we get is a surface of genus 4. It's the surface, nothing but the surface of genus 4. And one more nice property, so I will finish shortly. Well, anyhow, there's not much to tell. One more message is the following. Before we go to that, of course, this procedure holds for any dimension, for any number of edges. And one more message about this construction and the Permutohedron. So the classical Permutohedron is also remarkable because it is a zonotope. It is a zonotope, it is a sum of segments, and the segments, zonotope is Minkowski sum of segments. Minkowski sum of segments, and actually the segments can be very easily retrieved. So it's something very basic geometric things. And
does it correspond to something on the level of actually polygons, or is it just pure combinatorials? Again, it's all coming from polygons in the end. Is there some sort of explanation for all these remarkable things just by looking at why so like those?
well, that's very easy. It's just very elementary. So we should just well, it's So there is nothing deep which is considered. So it's, well, so the Permutohedron is a zonotope, and consequently all the faces of Permutohedron are also zonotopes. And what is nice here, what we patch in, the new faces, the diagonal faces that appear during this surgery, they are also zonotopes, which is not a complete truth. They are virtual zonotopes. Let me explain what does it mean. Okay, let's erase this. This is where I wish to be very, very vague, so if you excuse me. So this is the Permutohedron, Pn. These are edges living on its surface. And if you, more or less, if you take all possible edges without multiplicities and add them together, you get the entire Permutohedron. So this is a procedure for just any zonotope. So you just take the edges in an accurate way, and then you add them up, you get the entire thing. This is what for zonotope holds. Now, and basically you take these edges with, so to say, with weights equal to +1, with positive weights 1. Okay. Now, during our surgery, there appear some edges that did not appear as edges of the Permutohedron, the diagonal ones that correspond to cyclic permutations. And those should be weighted by -1. Those should be weighted by -1. And the message is that whenever something is patched, something diagonal is patched inside, so this guy, let us call it diagonal D, is the sum, Minkowski sum of plus edges, edges taken with weight 1 if they come from the boundary complex of the Permutohedron, or with the inverse of the edges if they are diagonal. And there is just one short. If you take this edge and you add by Minkowski this and add by Minkowski this, you get this. Weights are 1, 1, and 1. And if for instance, I put here the weight -1, you get something like this. You get something like this. So it's not honest zonotope, but still it is, in a sense, it fits nicely in the class of virtual zonotopes. The paper is available, so it is a preprint yet. It is available on the web, on the archive. Thank you very much for your attention.
Questions, please? So there is one more remarkable polyhedron here, namely, there are the triangular inequalities, or generalized triangular inequalities, which you impose to make sure that this model is based on non-empty.
Mm-hmm.
So they're just linear inequalities, and they define one more polyhedron, and always forget its name.
Associahedron. Association. Well, actually, there are very many related objects. For instance, the more appropriate thing is cyclohedron, because cyclohedron, it captures the combinatorics. So if we take the configuration space of unlabeled points on the circle, unlabeled on the circle, and you forbid them to glue together, there is a way of compactification this, and by putting brackets. And this is the associahedron. What you arrive at is called associahedron, and it is some convex polytope, So all of them live in the category of secondary polytopes, and so there is some hidden interplay which I still do not understand. So till now I know only very elementary things.
The model is related to the hyperplane arrangement for the Vincent diagram IN.
Yeah.
And then you go to the cyclic case, then it seems that you, in some sense, you go to Moduli.
Yes.
And therefore it has to be a corresponding hyperplane arrangement. But you still, so then we have to expect that it will be something with infinitely many pieces, because it's now Moody algebra, but nevertheless you stay with some finite objects. So maybe some, I don't know how to explain, but something finite in the infinite.
So you have some projects.
Yes, this is.
Because it's also has to be related to Moody.
Yes, but I should say that you are not the first who says such things.
Because if you consider hyperplane arrangement, then Permutohedron just has a normal fund, which is a hyperplane arrangement of full graph. So it is just a set of all the loops with ei minus nj. So this is that's what the gradient. But then you go to the second case. So it means that instead of Vincent diagram,
You just take cycle, yes.
yeah, but then you say cycle and you have Moody. And therefore, in some sense, also this is how you fetch this arrangement. So therefore, you just add.
Yeah, so it's better to postpone.
Yeah, but maybe not.
Well, I try to be more close to the remarkable talk. First of all, I want to say that just now I understand that the difficulties here is very similar to the difficulty of the topics which we studied maybe 10 years ago about convex lattice polygons, but the problem was about asymptotics. What's the limit shape of typical convex polygon? Lattice or not, let's say it's not important. And also it's very nice to, in that case, the main problem was asymptotics. And this is very interesting to consider asymptotic questions in your theory, and it's possible to do. And the question is the following: what do you know about three-dimensional case?
The proper counterpart for a three-dimensional case would be the following.
The difficulty is, of course, the same, because two-dimensional case, in a sense, simple because you have good parameterization of convex polygon, simply set of the edges, that's all. And in three-dimensional case...
Yes, well, literally the same. Looks like this. So assume that you have a closed, well, I have one more minute. A closed polygon in 3D.
Yeah.
So basically you have a collection of vectors that sum up to 0. Therefore, there is Minkowski theorem, which says that there is a convex polytope which has these very areas and these very directions. And the label is, so it gives us a label. So the label is the combinatorial type. And now, who knows what is the preimage of a label in the configuration space? So this is some Steinitz type theorem, probably, or maybe it's universality type theorem, because when you fix the combinatorial type and the values of the areas, it is, I don't know.
Something about, say, homology of...
Yes. Well, for the moduli space in 3D, there are Milson-Kapovich paper and Klechko paper, and so there is. Actually it's better because it's you live in the in the complex place, so it's scalar manifold.
Completely different.
Yes.
Very good and three-dimensional.
It's not divided in cells. You think of this as a roughly as a toric variety. I mean, it's not quite toric variety. Each
And
generation of toric variety.
Klashko explains how it can be divided by cells by the action of Hamiltonian, and but these are completely different issues.
More question, please.